So today I am going to talk about again the properties of nonlinear map. Here I will discuss the period doubling, attractor, and attractor is also known as cycle points, then bifurcation, and then lastly I will talk about the Feigenbaum constant. These are very interesting concepts in the nonlinear dynamics. So in the earlier lecture we learned that logistic map is stable. For mu less than 3, but for mu greater than equal to 3, the system of long-term population bifurcates into two populations. So let us see that how things will population, and this bifurcation into two populations is known as period doubling. Right? The system seems to behave like thus. System seems to behave like that. It is attracted by two populations and these populations are called attractors or cycle points. Right, so these are the two things which we have to keep in mind. One is the bifurcation of the population and another is the attractors. So let us understand this by taking in the case of the bug population. So consider the case of bug population again, which we have considered in the earlier lecture. So since we know that xn plus 1 is equal to f of xn, and similarly I can write down the formula for the xn plus 2. It is f of xn, and let me put the value of f of xn, because as we know that let me write down xn simply by f of x, and we know that the value of f of x will be mu x 1 minus x. This is the value of this part, and then again its function. So let me write down its value now. So its value will be, it is mu, in place of x we have to write down this one, so it is mu x into 1 minus x into 1 minus mu x 1 minus x. Right, so that's what will become now. So therefore it is equal to mu square x 1 minus x and here it will be 1 minus mu x 1 minus x. This is a very simple algebra which I am using, and if it satisfies fixed point condition, then that is xn plus 2. If I will write down it as x star or simply x, then how things can be written? I can write down as this x is equal to, means x is equal to mu square x 1 minus x 1 minus mu x 1 minus x, right? So let us do little algebra now. So this can be written as mu square x 1 minus x, and here it is 1 minus mu x 1 minus x minus x, it is equal to 0. So x can be taken outside, so it is x, it is mu x, sorry, it is mu square 1 minus x, and inside it is 1 minus mu x 1 minus x minus 1. This will be equal to 0, which implies that x is equal to 0, or the second part will be equal to this 1 minus x 1 minus mu x 1 minus x. This is equal to 0. Now if we try to look at this equation, this part, this is a cubic equation, and after doing little algebra I can make its factors, and its factors are like this: lambda minus 1 minus lambda x into lambda square x square minus lambda square, sorry, not lambda, but it is mu. So it is mu minus 1 minus mu x, and here it is mu square x square minus mu square x minus mu x plus plus mu plus 1, right? That's what we are getting. And this is equal to 0. Now these are the two factors and they are separately equal to 0. So from here I can write down that mu minus 1 minus mu x is equal to 0, or mu square x minus mu x plus mu plus 1 is equal to 0. So from here I can write down that mu minus 1 is equal to mu x, and from here I can write down x is equal to mu minus 1 over mu, and it is 1 minus 1 over mu, as I talked about it in the earlier lecture also. This is the another stable point. But if I try to look at this part, then this can be written as mu square x square minus mu square plus mu x plus mu plus 1, it is equal to 0. Now it is a quadratic in x square, and it's a quadratic, then I can write down the value, means I will solve this quadratic equation. And if I try to solve this quadratic equation, then what I am getting? So let us have a look at this part now. So it is x is equal to plus mu square plus mu, means minus b plus minus b square minus 4ac minus mu square plus mu b square minus 4ac. So in place of a it is mu square and in place of c it is mu plus 1 is sitting, and taking whole under the root divided by 2a, so 2 mu square I am getting. So mu is sitting here and it is mu square, and if I take square so it will become positive. So that means after doing little algebra I can write down it as mu plus 1 plus mu can be taken outside, so it is mu plus 1 whole square minus 4 mu and mu plus 1 taking under the root. Sorry, this mu will not be there because it comes outside, right, divided up by 2 mu square. So this is mu, so this will cancel out with this mu. So that means the value of x which I am getting, it is mu plus 1 plus minus mu plus 1 whole square minus 4 mu plus 1 whole under the root whole upon 2 mu. That's what I am getting here. And let me try to solve this part also. Let us have a look at it. So if I try to look at it, then mu plus 1 whole square minus 4 mu plus 1, it can be written as mu square plus 1 plus 2 mu minus 4 mu minus 4, and it is mu square minus 2 mu minus 3. So here it is mu square minus 3 mu plus mu minus 3. So here I can write down mu minus 3 plus 1 mu minus 3. So it is mu minus 3 and mu plus 1. So these are the factors of this. So therefore I can write down that x is equal to 1 upon 2 mu. It is lambda plus it is mu plus 1, then plus minus whole under the root mu minus 3 and mu plus 1. So this is the value of x which we are getting, and it suggests us two values, right? So thus I conclude that 2 points are given. Thus 2 means 2 points are given, and this suggests the bifurcation of population. With mu, right? So this is all about this lecture. So let us understand the concept of bifurcation or period doubling by doing a simulation of the logistic map, that is xn plus 1 is equal to x 1 minus x, it is mu. So let us understand it with the help of some. So for this I have written a very small code, and this I have taken from the book on computational physics by Landau. I am strictly following this for these lectures, right? And this is the code which I have written. And then I did two things, because initially there is transient behavior. In the initial there is a fluctuations in the population, and we call that transients. So here I have what I did, I have omitted the initial points. So I have recorded the points, 500 points means last 501 to 1001 points, and initial point means I waited to stabilize the population. So means these 500 steps I have ignored. I will tell you this, but I have also plotted this data, and this data is also, this y is in place of x and m is place of mu, which I am using, means x in place of y and m in place of mu. That's what we are using in this code. So let us have a look at it. So when I run the code, so initially up to 1, when the parameter mu will be up to 1, then the population stabilizes for the last 500 points, but for the initial points it changes, there is a fluctuation. So I stabilized it and then have a look at it, and then I plotted the same for 2, see the changes. So this is a way that how things will change for this, right? So this is for the last 500 points and this is for the first 500 points, and see, this is for up to 3.5. so no pattern will be observed. But when I ignored the beginning 500 points and I focused on the last 500 points, means transient behavior, after transient behavior I will see a pattern that it will bifurcate at 3, right? It starts bifurcating, and see, it bifurcate at 3, and after that it will bifurcate at this point around about 3.44, and see for the first points that no pattern will be observed, right? And then let us try to understand it now again. So see it now. Say, so this is the bifurcation diagram analysis. Let us call it as L0 or whatever you want to call it as. So not L0, but let us call it as mu naught, and let us call it as mu naught, let us call it as mu 1, and let us call it as mu 1, and let us call it as mu 2. So bifurcation will be occurring after some point, and first bifurcation will occur at 3 and another at this point. This point is 3.449, and another bifurcation will occur at 3 after 3.44, it is 3.544, and so on. This pattern will repeat, and after that there is a chaos in this region. This region is the chaos region, right? So if we try to take the ratios, like if I take 3.449, means if I take the ratio of this distance over this distance, means these are the points which I am taking, then I am getting a 4.72 nearly. And if I take another step, means if I take another population, means these, then I will take the it is also 4.66, right? So that means a type of constant number is emerging. So here I will call it as Li minus 1 minus Li minus Li plus 1, and here it is Li, right? So if I do like this, then this thing comes out to be constant. In some books this L is replaced by mu, whatever you want to call. So here I am using a mu axis, so that's why it is mu I minus 1 minus mu I over mu I plus 1 minus mu I. So keeping all these things in mind, that means a constant number is emerging out. And so what we are observing from all these, and this is the code which I am using. Sorry, this is the GNU plot script which I use to plot the data which I am getting, right? Now let us understand that what does it mean. That so from above analysis, we observe that that bifurcation occurs at mu is equal to 3, then 3.449, then 3.544 and 3.5644 and 3.5688 and so on. And end of the series is the chaotic behavior. End of it is a chaotic behavior, right? So from above we will get a pattern. So if k will approaches to infinity, means it is mu k minus 1 over mu k plus 1 minus mu k, and it comes out to be a constant number, and this is the constant which we are getting, right? This is a constant and this is nearly equal to 4.6692, and this constant is known as Feigenbaum constant. And for the given logistic map, I try to find out this constant, and this comes out to be nearly equal to this one. So if I try to look back, so that means this is more closer, 4.66 for the second population, and for the third and the fourth and so on, it converges to a particular value. So that's all for this lecture. Thanks for watching this.